This is Polarized Light Microscopy in Archaeology. And this is Lecture 8, Sediment Characterization. So sediments are very important things, particularly to the oil industry, because they're often full of oil. And so because oil money is paying for it all, there's a lot of work being done on drilling holes in sediments and studying them because they're trying to find where the oil goes. So one of the things they do with the drill cores is they look at the sediments. And so they do this by actually sieving all the sands and silts and coming up with these very close divisions of the inclusions within it. See, with one of these things, they put the sediment to the top, it rattles, and it settles down into the various sieves, and they can work out what the distribution is of grain size. So an aspect of sediment studies is maturity of the sediment. And what this means is the mineralogy, the variability in the mineralogy, the types of minerals, goes down. And so the softer minerals tend to get worn down, and what you have left are harder minerals like quartz. Sortedness goes up, and I'll be saying what sortedness is a bit later. And roundedness goes up. Roundedness sounds kind of obvious, but I'll give the details in this lecture. So here we have angularity going down to roundedness. And so the further downstream, it becomes less angular and more rounded. And this is quite logical, really. You start off smooshing something and it ends up getting quite round. Sortedness, however, is another attribute which is also, quite obvious when things are like broken right out of the mountain, shall we say. It will be very poorly sorted with big bits and little bits, but as it's worn away, the big bits get beaten up more and little bits get beaten up less. But what actually happens is, as it says here, sorting. And so as it goes further down, the stream will sort the grains into different sizes depending on the depositional regime of the flow that is carrying the sediments. And so it gets sorted into these shapes. It's not that somehow the universe decides, oh, all the grains should be the same size. It's the river will sort them into, say, beds of gravel and beds of sand and beds of silt, depending how fast the stream is going. So an example of that is, here we have the Tigris Euphrates Basin, and here are two sites. This is Tel Hadidi. Tel Hadidi is the actual word. The Iron Tel up on the Euphrates here. And here is Ur down here, also on the Euphrates. And you can see, looking at the mineralogy here, you have quite angular. This is probably more like subangular inclusions, but quite angular. And things like a lot of serpentine and volcanic rocks and all sorts of other stuff. Whereas when you get down to ore, there's a lot more roundedness, the grain sizes are more the same, and there's less diversity. Like there's a lot of quartz and feldspars in here, and that's about it. So that shows you that the maturity does actually work for the Tigris-Euphrates Basin. So sorting. So a sorted fabric has grains of more or less the same size. An unsorted fabric comprises grains of a diversity of sizes. The terms as defined by sedimentologists refer to rigidly defined parameters. So these are like involving lots of computer number crunching and stuff like that, and looking at lots of grains, and it's very important because oil is involved. But sedimentologists have developed acceptable comparison charts including the one in Petitjean Atoll 1987, which is in the manual. And so this breaks the rigidly defined parameters into 4 types: very well sorted, moderately sorted, and poorly sorted. And here is your actual Petitjean Atoll 1987 image. And as you can see, this is some sort of mathematical thingy, which I've completely forgotten what it means, because it doesn't really matter. We're just following the people who decide what is the way of deciding what sediments are, which is sedimentologists like Petitjean et al., and we're doing it their way, and so that is sufficient. So very well sorted, moderately sorted, poorly sorted. And although this is a very useful comparison chart, what is more useful, because this is what we call a grain supported matrix. So the grains basically are sitting on top of each other, which is not what we get in pottery, which is more matrix supported. Yeah, there we go. So I actually used that and used a graphics program to make it more look like pottery. So we have the matrix here and the grains floating in it, just like we have inclusions in pottery. But it's exactly the same, only spread out. So this is based directly on the Petitjean data and with the same terminology, but it works better for pottery. So there you go. So this is in the manual. So grain size. Unless subjected to processing by humans, because we're talking about archaeological pottery here, and so humans may actually mess around with stuff, the size of a grain is related to the degree of weathering and erosion it has been subjected to. Its collection into a raw material deposit that can be utilized is dictated by the environment in which it was deposited. So a slow-moving and meandering river is more likely to deposit fine sands and silt. A high-energy beach deposit, for example, will deposit well-rounded, mature sands, whereas a swiftly moving mountain river is more likely to deposit cobbles and coarse, immature sands. So back to this fun diagram. So basically, when it first comes out, you've got a lot of unsorted angularity and all that sort of thing. Things just knocked right out of the rock. And as it gets further down, you get sortedness and roundedness and this sort of thing. So the analysis of grain size in thin section, I base my analysis on the work of some colleagues at the British Museum, most of which I think are retired by now. This was published in 1985. They got this new device which enables them to basically measure on the computer. This is back in the early 80s, so it was quite simple stuff, and work out the best way of measuring grains in pottery to see how many you need to measure to get appropriate data. So again, this is from their publication, and they looked at various techniques, and also, like, this is point counting, going from point to point to point. What is under the point? What is point is gets counted. Yeah, there you go. So the white one is counted and the black one is not counted. It's not under a point. And there is the area. The line. So here it's following the line. What is in the line gets counted, and what isn't in the line doesn't get counted. And they did the area, so the entire area you're looking at. They also did a ribbon count. So that's going across with a ribbon shaped sample, and anything above the line is counted. You know, starting within the ribbon, but going above the ribbon is counted, but anything that goes below the ribbon is not counted. So it has to be either entirely in or going off to one side. And so this is largely the technique we're using, but we're doing it by having the area and moving it along. So if this is the thin section and this is the field of view, we basically go along the field of view, all these circles of the field of view, and we look and we measure all the inclusions which are either within the field of view as we go along or go above it. So this one we have to like pop out and do it. So the objective of doing this is to come up with a graph, and I've always made these block diagrams, and a thing about the blocks is that they're very clear. You can like do interesting things to look at the minerals, diversity within it. Not very statistically valid, certainly not as valid as the actual grain size distribution itself, but still quite informative. And when you do it as a block anyway, as opposed to a line graph, then you can actually just do what I do. I've always felt that it is pointless to collect data you do not intend to publish. So measuring every grain and then working out this graph from that is a lot more work, unnecessary work, than just sort of eyeballing which of the columns it belongs in. So this is the Graticule, which should be inside your microscope. It's certainly inside my microscope if you get to look down it, if you have to look down it. And you see it goes from 0 to 10, and here it is 0 to 10. And so if you're looking at the appropriate magnification, which is 10 by 10, so 100 times magnification, this should be the dimensions we're looking at. So this is millimeters, 0.250 millimeters, and everything above, you see, so everything above. And so then what you do, instead of looking at a grain and measuring it, you decide, is it like about this size? Or is it about that size? Or is it about that size? So if it's about that size, you put a tick in here, or a line. I usually do one of those gate-like measuring things with like 1, 2, 3, 4 cross, and so make 5 and do another one. And so you do that until you've counted 150 grains. Okay, so you need to do that until you have 150 things done here. These lines here, as if you want to do looking at different minerals, then you will want to do different orders. So this might be quartz, this could be feldspar, this could be something else. And so then what you need to do is total them up and divide it, recalculate it basically until it makes up 100, because you want it to make it 100%, not 150 divided by whatever. So you need to recalculate these numbers, these 150 grains, or about 150 grains, down to 100. And then you plot it on here. And here you can create a graph rather like this. And that is the lab for doing the grain size. So it will come up eventually with things like this, which enable you to distinguish between different fabrics, petrofabrics, based on their grain size distribution, and also at times the minerals within them. Although, as I say, the mineralogy is not actually statistically reliable, although it is quite informative. But the grain size distribution has been shown to be quite valid, or not quite valid, just valid. So, of course, we have the good old grain size classification, more useful for description than actual any sort of reporting of the data, which would be better as a graph. And we have the Folk 1980 designations, which is typically what I get people to use. But you also have the International Grain Size Classification, which is not so very different. So, roundness. Again, much of the criteria for the sedimentary text is aimed at whole grains and other such sedimentological concerns, e.g. Pettijohn et al. 1987. So this is Pettijohn again. And so if you go back to those sieves, you see what they're quite often doing in these oil reserves is they're drilling down and coming up with solidified, indurated sands which have not been turned into rock. Basically, it's not sandstone; it's just sand. And so they're looking at this and they're wanting to determine how angular and rounded it is. And so they have very angular, subangular, sub-rounded, rounded, and well-rounded. But these are grains, not thin sections, so you're not being cut. And so I've modified this to this. I'm not entirely sure what very angular can be. I mean, angular is angular, and I'm sure it has meaning to sedimentologists looking at grains, but it doesn't work very well for me. So what I use is that basically you have angular things, which are very angular. It's freshly broken right out of the rock. Someone like whacked it or something, and there's a piece of very pointy rock or mineral or something. So it's broken, sharp, jagged edges, that sort of thing. So then you get subangular, which it's just get a little bit worn on the edges. You start getting, it's actually been in a stream and gone a bit of distance away from the source. And typically angular things have very probably been added to the clay paste. Subangular are things which were in a stream at some time. Then you have sub-rounded, so there you get more wear of the edges and it becoming more rounded, but still you have these angular aspects which show you that this is sub-rounded, not rounded. So rounded is, it's pretty well rounded. Not well rounded, but it's quite rounded. And so it's rounded, but there'll be embayments like this, you see, and a bit of a straight line here and there. So it's rounded. Everything's been worn somewhere a little bit, but it's not well rounded. This is well rounded. So well rounded means it's all rounded. There's no embayments, there's no straight bits, it's just everything has had a good rounding. And so that is description. And of course all of this is in the manual. So then we have abundance. So abundance is basically how much of an inclusion there is in the thin section. Basically the entire pottery is 100%, and you might want to say 5% is biotite, 10% is plagioclase. That doesn't actually reflect how many you see in this actual picture of a thin section, but like that expresses a total percentage of the body. So I've always found it best to avoid simple word descriptions, which you will see in the literature, such as abundant and scarce, which are not defined, and it's very difficult to then, if they don't define it, which typically they don't, to compare your thin section and to say, well, is that what they mean abundant, or is that what they mean scarce? Because maybe you're more abundant, and your abundant is their scarce. Who the hell knows? And so it's better to have these actual numeric designations. And the way I do it, which I learned when I worked in the geology department at the Royal Ontario Museum, is to use abundance charts. And by doing this, you compare these charts to what you have, and you say, oh, that's about 1% or 2% or maybe 20%. And by this you come up with a number. And how I actually did this working for my head of department back in the early-ish 80s was to use point counting. This is how point counting works. And so what you would do is you have, I'll just go to the next one, you have these things, actually these things. And so this goes on top of this. This is the stage that goes around on your microscope. And this mount goes on top of that. And you put the thin section in here. And as you turn this, it goes along a notch. Click. and it has a little thing that makes it go click. And so it goes across, and I go back to the previous slide. So that click goes from here, click, 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 and every click you say what is the type of mineral. Here's a quartz, click, there's something else, click, there's something else, click, there's something else. And what we were working on were metamorphic rocks. It looked a lot like granitic rocks. They were, and the grain sizes were pretty much all the same. And so the click of that device here worked out very well for it. It's calculated for the common type of grain size you get in granitic rocks or metamorphic rocks. Because you actually need to do this properly, you need to calculate the count interval that you're working with. You can't just go any old interval that you like. The interval has to be calculated based on the grain sizes you have within your fabric. And so all the people that just throw it on the microscope and go click, click, click are doing it wrong. It's just completely wrong. Another thing is when I did this for the geology department, I counted 1,000 points. That's 1,000 points. And so that is a lot of points. And so if someone is saying, oh, I'm doing point counting so I can get accurate data, and they're not doing 1,000 points, they're not doing that right either. So unless they calculate the interval of the counting, and unless they do a significant number, and I don't mean like 100 or 200 or something, they're doing it completely wrong. And the thing about the abundance charts is that once I had done all of that work, counting 1,000 points, my head department would then look at the thin section down the microscope and compare it to an abundance chart to make sure I got it right. He wasn't checking that I'd done it. The problem is the difference between precision and accuracy. These are accurate. They just don't seem very precise. And so he would look at these charts to make sure that my data was more or less right, and so we could pretend that precision was also accurate. So I thought, why on earth am I wasting my time? We should just do this. And so that's the technique we use here at the ROM. And so that is it for our studies of sedimentology. Hopefully you'll be able to get to do that in the labs. Thank you.